Okay, I'm going to take you through the relationship between this unit circle that you're probably familiar with from calculus and trig, and the real space of an oscillating spring a little bit more carefully right now. One of the things I did here was I started off at a maximum amplitude. So this original position I'm going to call x, if I can draw an x max, which I'll set equal to a. So this is our amplitude. And that's the greatest distance it can be from what we call the equilibrium. So this right here would be equilibrium. Right there, if I can draw my arrow on the right line. So this is our equilibrium. This is important because it's actually where the sum of forces on the object is going to be equal to 0. So wherever there's no net force on the object, that's where our equilibrium is going to be. So for this hanging spring, it gets a little bit complicated, and we'll go through it a little bit later. But it's not too bad. Just the idea here is that there's not going to be any acceleration when it gets to this point. And what we'll do is we'll kind of take it through a quarter of a cycle. For the spring to go from up here down to here is a quarter of a cycle. If it goes down the other way, down to its maximum displacement down here, that would be up to half of a cycle. So that would be corresponding to somewhere around here. If it got down to around there. And then if it got all the way back up to here, that would be the full cycle. So half of a cycle gets us to the other max. So this would be, this x down here would be equal to the opposite of a, the opposite of the amplitude. And then to get the full cycle, we have to go all the way back up again to the top. There's a couple different ways to parse cycles, to break them up, but we'll just focus on this way for now. One of the things that I want to draw your attention to is the difference in the distances traveled in each case. So in the first segment of time, keep in mind that we've got this green point here, and it's going to travel around the circle at a constant speed. Okay, so we have this nice uniform circular motion. And there are a few things in the world that are actually simpler than circular motion. You guys might disagree after taking the circular motion unit, but it's really a pretty simple motion. It's standard, it's going to go at constant speed, has a nice period, so it's pretty easy to deal with. An oscillating spring is a little messier. You can see it speeds up, it slows down, so why not use something that's going at a constant speed as your mathematical model? And that's basically what we're going to do. We've got this messy real-life situation, but for the math of it, we're going to use something that's very nice and easy, a circle. So this is for math. Okay, that's the reason why we do this. And in this first segment of time, so we'll just assume that I'm looking at equal segments of time. So from here to here is one segment of time, here to there is another segment of time, and then to the equilibrium is yet another segment of time. And I've broken this up into equal angles. So I have one angle here, I have another angle to here, and I have an angle to the equilibrium, and all of these angles are going to be identical to each other. So we're moving through, I would say, 30 degrees in each case, or yeah, 30 degrees. And so it's moving at a constant speed. This green dot is moving at a constant speed at all times. But if we look over at the spring, if we look at it from our edge-on view, so if we're over here, way over here, looking at this, okay, viewing what's happening, we see this green point actually only moving a little bit. And that corresponds to the little bit that the mass moves on the spring. Why does it only move a little bit? Because it started up here. It's starting from rest, and the spring and gravity are both pushing it down. So it gets to this point, and now it's already got a certain amount of speed, and it still has some force on it pushing it down, so it's able to cover a greater distance. And when we look at this last segment, it covers a little bit of a greater distance than that time. Why? Because it's already going at a decent speed and it's still being pushed downwards. So we have these downward pushes that accelerate the object and get it to go faster and faster and faster. What happens down here is exactly the opposite. You would end up getting, so if I look at this in terms of forces, the force view of things is going to have a big downward force, a big downward net force, and then it'll have a smaller downward net force because Well, the spring just isn't compressed as much anymore. So we're going to get a smaller downward force, and then when we get down to here, we're going to have an even smaller downward force, because the spring is now, at this point, maybe even starting to pull up a little bit against gravity. And the same thing happens as we go to the other side. So we get a little bit of an upward force here, mostly due to the spring, or actually entirely due to the spring. We have a larger force here, and we have the largest force down here. So we have these forces that are constantly trying to get the object to go back to equilibrium. That's the whole reason why this simple harmonic motion takes place. We have an object, it's moving, and we try to shove it back to equilibrium. If it moves off to the one side, we shove it back. If it moves off to the other side, we shove it back. The problem is that we're so busy shoving it towards the equilibrium that by the time it gets to the equilibrium, it has a lot of speed going. So that's the idea behind physically what's happening with the spring. Now mathematically, we can just take this and very easily break it up into parts. So I can find, and it's actually probably easiest to do the speed. Okay, if I do this here, we'll start with this. We have a velocity off to the side, and I'll call this v1. And v1 in the y is equal to 0. Why? Because it's not going in the y at all. If I look at the next segment, it's the same v, it's the same size v. Okay, just a different direction. So it's off to the side, and I'm going to draw it down here. Actually, I'll draw all of them down here where I've got a little bit more room. So this was the first one. v1, where v in the y, v1 in the y equals 0. Then we had our next one, which is at a 30-degree angle. So it's sort of like this, same size, and most of it is still not going in a direction that helps us out. But we have v2 in the y is equal to the overall velocity times the cosine of, well, it depends on how you want to do it. So this is the same as that angle right there. Okay, this is my 30 degrees. So what I can do is I can do sine then. So v sine of that angle. And that's pretty straightforward. So this is my 30-degree angle, because I'm off by 30 degrees from the original. And so this would actually be v sine 30 if I wanted to go that far. The next one is at an even steeper angle. It's at a 60-degree angle. So the amount of the velocity that's not visible to us is much larger, and this would be then the 60 degrees, because it's 60 degrees from here to there. So we'd have 60 degrees, and my velocity here in the y direction would be v sine theta once again, or v sine of 60. And the last bit, the final segment, let me draw that up here. The last bit is just straight down. So I draw this one, and the v4 in the y is just equal to v. Now we could take it through and say it's equal to v sine of theta, where theta is equal to 90, and so I just get v. Okay, so we're going from 0 to v, 0 to the maximum speed of the particle, or the full speed of the particle, and we hit that full speed right here, right at the equilibrium. So once we get to the point where the amplitude is 0, so we're at 0 amplitude, we have a maximum speed. That's also where our acceleration is 0. Okay, now the reason why we do this is because we can construct equations then, and for every oscillator we can just construct these fairly simple equations. You know, if I want to know what the velocity is at any particular time or at any particular position, it might be easier to think about it in terms of positions right now. I can just do v out of a certain position is equal to the maximum velocity times the sine of the angle. And the same thing would be true for the position. Only it's going to be cosine of the angle instead. You know, right here, if we're looking at this being a 0-degree angle, we have a maximum amplitude. Here where we have the 90-degree angle from the original point, we have 0 amplitude. So our x would be 0 at that point. And we can do the same thing with the accelerations. So what we get from converting the real space into the phase space and vice versa is we get a simple model, mathematical model to work off of that gives us some simple mathematical solutions to apply to any simple harmonic oscillator, whether it's a spring or a pendulum or anything of that nature. Hopefully this helps you to see the relationship between these two, because it is of fundamental importance. We're not going to be focusing so much on this in the future. I'll bring it back a little bit, but we're going to be doing a lot more with just springs in general and more of an experimental basis next.